On. Okay, so class, we have our first test Tuesday. I learned during class period, so it will be a lot of thermodynamics. Yoo-hoo, doesn't get any better than that. I mean, that's real fun right there. But it will also have utility rate structure. I'll let you. I'll probably give you some piece of or some utility data and ask you to calculate, not the whole bill, but I'll pick out something, you know. And yes, sir.
So we'll have the class period completed?
What's that?
We'll have the class period.
Yeah, it'll take up the whole class period, and it'll, you know, basically you'll have an hour and 20 minutes, and I'm going to give you a pretty tight window to sign in so that everybody will get done about because what it does is you have a window to sign in and then you have, you know, the allotted time after, so long as you sign in during that window. So
is it going to give us a question if we write it on paper and upload that, or is it going to be online?
No, it's going to be online.
Okay.
Yeah. Heavens.
So it'll have an answer box to put stuff into?
Yeah, it'll probably be multiple choice. You know, I'll give you a little piece, you know, I'll give you little thermal problems around the cycle. I might give you a pump and an isentropic efficiency and okay, here's the pressures, here's what's coming in. Tell me the amount of work or something like that. And then you'll have 4 or 5 answers, or maybe 7, 8, 9, 10 answers. You get to select the right one. And then there'll probably be some true false. But there'll be rate stuff and there'll be power factor stuff. I'll go back and review any videos. I don't know that we did a whole lot of videos that I would pull into this, but I'll send you an email. I need to go back and review. I don't remember exactly all the links that were sent out. You know, because all the renewable stuff is in your presentation. So, you know, that's kind of like double jeopardy. And I'll just have to go check. I don't remember exactly right now. I've sent out stuff to both classes, and as you can tell, I get sometimes confused between the two. So that's the biggest news Tuesday. And then we're going to continue on. I did send an email to TVA today, a few minutes ago, to my friend Ronald Dinkins, asking if we could do a tour. So, you know, it's an old coal plant, but it's still, I mean, when you've never been in a power plant, it's still pretty cool to look around. You know, and again, the only thing that's different is, you know, as coal goes away, the boiler will go away, but still you got to have a heat source, and you know, you get to see the turbine floors and feed water heaters and, you know, the stacks and all the fans and the pumps, and you know, there's just a real appreciation for the scale of this thing. It's hard to imagine until you walk up next to a, you know, 3,000 horsepower motor driving a boiler feed pump or something, or 2,000 or whatever they are. They've got them from, I think, 1,000 to 3,000 horsepower motors pushing stuff, and you can see the emissions control stuff, some of it. And going to the control room is pretty cool. You see all the, you know, how the operators control things. So, I mean, it's certainly it's basically a half day. We usually get back maybe 1 o'clock. We leave about 7. So that's 8 their time. They're on Eastern time. So it's about an hour and 50, maybe an hour and 30 minutes to get in. So 8, 9:30, 10:30, 11:30, 12:30, you know, maybe 1 their time, which is 12 our time, which then puts us back here about 1:15 or so, give or take. And then it is possible, if we can go, it's possible to drive yourself. So sometimes students will say, man, I got to be back for something at noon. Well, you can drive yourself. We all show up together, and then you can just split off and, you know, leave early if you have to. So that's a possibility, but we'll see. We'll see what they come back. I'll let you know. I'm hopeful that we can go back this year. Okay, so we're going to finish up, you know, my comments on the boilers here, and you know, there's some pretty good information here. And then we're going to move in. I sent out, we move into a turbine article, which is centered around stresses, thermal stresses. How can you basically wreck a turbine, a turbine or a turbine rotor? And that it involves a little bit of fracture mechanics, and so we don't do a lot with calculations, but we talk about some of the concepts on fracture mechanics. And that'll be our next block of the course. So anyway. Okay, so let's go ahead and look at this. Let's see, if I go back last time, we were kind of working our way through this, and I was just talking from some of these slides before, and I think we talked past this and the headers and all that. And I think this is where we wound up was, the different, based on the type boiler. Can you read sideways? Oh, I guess I can rotate it. I guess I'll do that for you. Okay, so based on what you're generating, if just, low pressure saturated steam, kind of an idea of the percent of the total heat absorbed that goes for different purposes. And of course, the utility boiler is way over here. And it shows, we put in, we got to heat the water to saturation, we got to boil it, we're going to superheat it, and then we're going to reheat it as well. So all significant energy users. And that boiler, I did find the rotate, so I can go get counterclockwise now. Okay. So this is where we are next. I'm going to pop back and forth between the notes here. Let's see here. Let's go up, make sure I get to the top of this. 11. Yeah, that was steam conditions. Okay, so, this is in terms of generating. And so we're going to generate this steam inside of these small diameter tubes. And the note here says 1.5 to 3 inch diameter tubes. And so they're going to line that furnace, and they're pretty much packed right up against one another. And that, so if we look on this, we got really two different types, two different ways this can be set up. Ooh, on that thing. This computer likes to blow the screen up on me. And so you can see the drum boiler, which is what we've been talking about so far, which I think the vast majority of the boilers that I've run into out there are drum boilers. And so, this is the steam drum up at the top of the boiler. And, this thing is maybe 3-4 foot diameter, and it's maybe 7,500 feet long, and it's it's seeing the saturated pressure. It's seeing the high pressure. So it's a thick wall cylinder, and it has the steam separators and some other components in there. We can introduce feed water into it. You can introduce chemicals into the drum, that sort of thing. So drum is a really key component. Another thing, and we'll run into this below, but as far as a control parameter, that water roughly filling half of the drum is a reservoir of water at the top of the boiler to keep water flowing through those tubes. Because if we continue to fire and we don't have water in that drum, that boiler will before long run out of water and it will melt. It will absolutely destroy itself. And so, and even if you're firing hard, and say something was to happen and you lose your water supply at the top of that thing, even if you stop firing, you've got so much heat in the tubes that's already been absorbed in the metal that you will damage components if you don't have a continuous flow of water through there. So the boiler guy, the efficiency engineer and all, the performance engineer is looking at this boiler as a steam producer. Well, the boiler guy is more concerned with, he wants to produce steam, but he's more concerned with a good flow of water through his tubes to not damage, all those components. Okay, so it's kind of two different perspectives on things. So that drum level, if you had to pick one parameter to measure on a boiler to make sure that you weren't going to blow up or something. Certainly one of the key parameters would be drum level. It's that important. It's in the top 2 or 3 parameters. There's some other things. You got to make sure that you've got your enough air going in. If you got all this hot fuel in there, if you don't put enough air to burn it in the furnace, you could cause a explosive condition. And you know, back in the old days, boilers used to explode. In the 1880s, 1890s, one of the leading causes of death in the U.S. was boiler explosions. I wasn't very comforted. You know, if you lived in a big building that had a boiler in the basement, you know, that's not good. And that's one of the reasons of the rise of ASME and all the boiler and pressure vessel codes was to stop killing so daggone many people with boilers exploding. And every once in a great while, there's still one that explodes. You know, I should check YouTube and see. I know there was one in Tennessee. Was it Dyer? No, it wasn't Dyersburg. Paris. It seemed like it was up around Paris, Tennessee. That this was 4, 5, 6, I don't know, 7 years ago, something like that. They had a partial explosion on natural gas fired boiler, and it it took off, ripped itself loose of the piping, went through a wall, and wound up in another part of the plant. And I don't recall anybody being killed, but let's just say it was a pretty exciting time in the plant, you know, when the boiler decided to explode. You know, on assessments, we have gone out and put our combustion analyzer into the stack, which is measuring flue gas. And I think ours will go offline at something like 4,000 or 5,000 parts per million of CO. Well, if you put a combustion analyzer offline with CO is a fuel. CO is explosive. And the only way you're doing that is you're burning all this, and it's natural gas. You're burning natural gas and you're not putting enough air in. So it's incomplete combustion. Not only is it poisonous and deadly if you breathe it, it can explode either coming out of the boiler or in the stack, or, you know, it just takes a good point of emission and you got an explosion. So I'd say 2 or 3 times we have stuck that combustion analyzer in, and that thing, you know, I mean, you just see the levels go up, and all of a sudden the instrument it shuts itself down for internal protections. And you start saying, whoa, you know, you better call your boiler guys now. Not in 10 minutes, but call them now and get them over here. And because you're starving this thing for air. And so the linkages or whatever, the controls on the fan are screwed up. Something's not right. So anyway, that stuff doesn't happen very often, but it does happen. And the vast majority of the time, it doesn't cause an explosion. So anyway, the discussion here, yeah.
You said the one thing that you would want was what?
The drum level, making sure that we had the proper level of water in the drum. See the picture up there, it shows it about 50%. So, I mean, they've got a scale like a big ruler or something, and it shows them, you know, like, here's the maximum and here's the minimum water level. And, you know, they want to keep it someplace comfortably in between. And so they're sitting there, and that's one of the control parameters, you know, because, you know, the firing rate on the boiler changes, the steam demand changes. And so you've got controls that have to feed more or less water into that drum. I mean, you can't fill the drum all the way up. You know, you have to keep it at the proper operating range. But that reservoir of water is safety to not overheat your boiler tubes by starving them for water. And it also, the right level, you know, that's additional downward pressure, you know, pushing water down through those tubes. And you know, the drum is operating. Of course, your feed water pump really establishes the pressure in there. Okay, so the distinction here is, I guess, between a drum boiler on the left, and see, you know, the water comes out this pipe on the side, and it goes down what they call the downcomer. We'll see in just a second. It goes down to the headers, and then it feeds water up here. And as the water gets up, you know, the fireball's over here. This is where the big heat flux is coming in, mostly radiant. We start boiling the water in here, and that boiling water reduces the density over here and tends to want this, because this is all solid water on the backside. So that tends to make this thing want to circulate on its own. We'll talk more about that in a minute. The other type boiler is what's called a once-through. And supercritical boilers are this type. But it doesn't have to be supercritical. So what you do is you have to control this water flow rate and the heat input flux at the right rate so that all of this water is turned to steam as it exits the water wall tubes. And then it just flows on for superheating through the superheat sections. On this side, see, this is the steam coming back up to the drum, and then we've got steam water separators in the drum. We'll see more of that later. And that steam is separated, and then the saturated steam goes on for superheating. And it's probably 4 or 5% on the low side, up to 33, 35% on the high side, gets evaporated, and the rest of the water is just going around in a circle, okay? So we pull the steam off and the water continues to recirculate, and then we add whatever water we need to maintain drum level. Okay, so that's the way it works. So two different concepts. It's like, you know, you go to the car dealership, do you want a straight stick shift or do you want an automatic transmission? Well, you go to the boiler company and you go, well, you want a drum boiler or you want a once-through? You know, there's just two different animals. Most of them, like I say, at least in my experience, are drum boilers. You know, Kingston's drum boiler. Okay, but because of the nature of supercritical, you know, when you go above 3208 psi, then you put heat in, and that phase change is just all kind of from liquid to vapor, but it doesn't boil. It's just like this. It changes. So kind of by definition, a supercritical boiler is a once-through, okay? And that's a good test question. You know, you can make a true-false out of it, something like that, or, you know, try to do something tricky, you know how we professors are, trying to trick you out there. So I think I pretty well got that. There's some notes on there. Subcooled water enters the tube, it's heated. Water flows through, steam form, most boilers. Steam water mixture enters the steam drum where steam water is separated, water is mixed with replacement and returned to the boiler. And so that temperature and pressure, that's Kingston. And actually they're 1815 psi, but they're because you remember that's either they're 1800 psig, so there's a mistake in my notes, but at that point 15 psi doesn't make much difference. And so their saturation temperature someplace around 621, maybe a little bit higher at 1815. That's talking about the once through, you know, so we control that flow rate and heat transfer rate so that all gets vaporized. And so if you have the once through, you don't need a steam drum. There's nothing for a steam drum to do, you know. And so, and then the note there that the flow cools boiler metal to prevent damage. That's an important point to realize. Just having that perspective on it, that, hey, we got a lot of money in this boiler, and we got to make sure all these heat transfer surfaces don't overheat and damage the metal. Okay, so circulation, you know, flow cools boiler tubes, we said that. Water must continuously circulate through the tubes. We can do it with natural or forced convection. Okay, so we're kind of learning about different distinctions in boiler types. So we got drum boilers and once throughs, and now we're going to have natural or forced circulation. Okay, So on the left is the natural circulation, and it's showing all of this now in terms of drum boilers. So you see you got your drum up there, and they even kind of roughed in a steam separator in this picture. You got your feed water in and all that. So that downcomer is the pipe that takes the water down to the bottom of the boiler, and then there's headers down there to distribute it. But so that's just saturated liquid coming out of the drum. Okay, so that, and it's not in the furnace, so it's not exposed to any heat flux. There's no heat input to it. So from A to B, that's, those tubes are all just full of water, saturated water at whatever the drum pressure is. Well, yeah.
So looking at this diagram, where do they add more water in? Because it's not.
You see up there at the top of the drum, it says feed water in. And, these types of diagrams, they might easily leave that out, because that's not what they're trying to illustrate. But no, I'm glad they put it in for sure. Okay, and so then as the water, comes across the bottom, heading to the left, and then starts moving up the tube on the right, it starts being heated, and it's saturated, so it doesn't take much heat input before we start forming vapor bubbles. And so the vapor bubbles then spread out, which makes the liquid and vapor on that side way less than the solid water on the downcomer side. And so all of a sudden you've got a density difference from the tube on the left to the tube on the right, and that density difference will push that water right on around and back up to the steam drum. And so it will circulate naturally. Now, you guys do have these figures. I've already sent them out to you, so you can do a quick sketch or something, and then get your notes down, and then refer back to the figure that you have. And so we'll list some characteristics here in a minute as to how we can increase what could you do to increase, or what are some effects that could decrease that natural circulation rate. But that would be an important part of a boiler design, because if you don't get the right circulation rate, then you're not going to have a chance to generate the correct amount of steam. So a lot of design work goes into making all this work correctly. Okay, so on the left we have natural or thermal circulation loop, and we don't have to pump it. It just circulates on its own. Well, that's good in some respects, right? Because you don't have a pump that can break down. If there is no pump, if it just happens because of nature and God and the laws of physics, well, that's a good thing, something less to maintain, less parasitic energy has to go in to run the cycle. So there's a lot of good things involved with a natural circulation boiler. Okay. On the right, however, we can put a pump in there. We can push. We push a little harder, then maybe we can make the thing a little smaller for the same capacity. And that's one reason they've gone to the forced circulation, is you can make the boiler a little bit smaller with less material and get the same capacity out of it, because you can push a little harder, get a little higher velocity, get a little higher convection coefficients, and all of a sudden you don't need quite as much material to generate the same amount of steam. Okay. But, so we have those advantages and the disadvantages. Yes, the pump can break, and you better have a backup pump or something, or you're going to be in trouble. It will still circulate some by natural convection. So you probably wouldn't have to worry about melting the tubes or damaging the tubes if the pump went out, because you could natural circulation enough for that, quit firing and just let it naturally cool down, and you'd be okay. But you wouldn't get nearly the same capacity out of it. So that's forced circulation and natural circulation. And let me look here. Oh, and here's a note. This heat rate, this is a general power plant term. I don't know why I wrote it here, but I did. And so basically a heat rate is, it has units on it, okay? So it's a number, it's the BTU input, say in fuel, or it could be hours. It could be, that would have to be, well, it's got to be a rate over a rate. So I guess that should be BTU input rate, BTUs per hour, you see the units, divided by K to generate 1 kW of power. So that's kind of like a 1 over efficiency with units. If you make that dimensionless, and you know what, 1 kW is what, 3413 BTUs per hour. And so you can use that conversion to make that dimensionless, and then you have to invert it because an efficiency is output over input. This is input over output. So this number you want to be as low as possible. But heat rate is used throughout the power industry to describe efficiency. Okay, they don't usually talk about our system's 32% efficient. They'll say, well, the heat rate, a good heat rate is like 9,500, something like that. Let's see what that is. If I take 9,500 BTUs per hour per kW and divide by 3413, I get 2.78, and then I have to invert that 1 over. And so that's almost 36% efficient. And for a coal plant, or for one of these, you know, not doing cogen, not combined cycle, that's a pretty good efficiency. They're not that efficient these days. So a bad heat rate would be something like 10.5, 11,000. So if you take 11,000, oops, and again, divide by 3413 and invert it, that's 31%, okay? Which obviously is not as good as 36%, you know? So heat rates below 10,000 are considered to be pretty darn good. Heat rates, you know, a lot, you know, 10, 5, upper 10s to 11 to 12, not so good. Okay. And of course, what usually happens is when the plant's at full load, it's more efficient. When the plant's starts throttling back to 50% load or something, then the heat rate will go up. Okay, so I think we talked about all those different sections in there. Less dense, so you know, natural circulation is caused by the density difference of gravity pushes around the loop. Okay, so here's some things that affect the rate of circulation. You know, if you were designing a new boiler and you wanted more natural circulation, you wanted to up the number, or what are things that affect it? You know, first you can make the boiler taller, you know, so if you make it taller, you got a longer length of tube with water on one side and steam and water mixture on the other side, so that will tend to increase the circulation rate. So here we'll go down here. Taller boilers produce a larger total pressure difference between the heated and unheated legs, implies larger total flow rates. Okay, so now what do you think? If you up the pressure, if you took the same boiler and increased pressure, would that increase or decrease your circulation rate? You might want to venture a guess. I love having live people in the room that can venture guesses and stuff. You see, I mean, you just got to know how to think about it. So the answer is increase in pressure causes decrease in circulation. And what happens is you increase the pressure, the size of the vapor bubbles decreases. And so the density on that heated leg, it increases. And so your density difference decreases because the density on the downcomers pretty much the same. But when you start increasing the drum pressure, the vapor bubble size is smaller for the same steam flow rate, which means that you have more water and less steam. So that's going to tend to reduce your circulation rate. Interesting. So that's what this one says. Operating pressures provide higher density steam and higher density steam water mixtures. This reduces the total weight difference between the heated and unheated segments, tends to reduce the flow rate. So that's kind of interesting. What else we got here? There's critical temperature and pressure. I got stuff written all over here. Okay, we can increase the cross-sectional area, have bigger diameter tubes. Now that may have some other impact on the heat transfer, you know, the surface area and all that sort of thing. So, I mean, a lot of the stuff's chained together, but just in terms of circulation rate, you know, if you have the same elevation, you have a larger diameter tube, you're going to have less frictional losses, you know, and so that would increase your circulation rate. So that pretty well makes sense. So I think is that, I had 4 things listed. Did we talk through all of them? Oh, yeah, the heat input rate. I don't know if I wrote a paragraph on that or not. So, I mean, if you put more heat in, you're going to form more steam, and so it should circulate more quickly. Okay. Cross-sectional area. Okay, so this little paragraph is talking about on a typical drum boiler, natural circulation, the amount of steam produced is, let's see, amount of water entering into the tube can vary from 3 to 25 units as far as steam. But anyway, that's a 4% to about 33% evaporation rate. So that's kind of typically the range that we operate in. So, you know, we defined forced circulation. We're going to add a pump, and we're going to push it around. And then this is the point about once we get above the critical point, it operates as a once through. The temperature continuously increases with heat addition. So, I mean, we just don't have the boiling. There is no boiling at pressures above the critical pressure. So for supercritical boilers, drums, steam water separator is not required. Boiler operates effectively as once through. We mentioned that. Let's see. Well, this is just working our way around the picture, which we kind of already did before. So I kind of jumped ahead on that, but I mean, I think, see, that's industrial. There was a good picture here back here. Those are Kingston units. I think this was a pretty good picture. So that's where we are in the notes, where we talk through all of this, but we did that the other day. So, you know, I don't think I'm going to do that again. But, you know, you should, I want you to be familiar with the flows through the boiler, some kind of an idea. You know, we have an air circuit and we have a water circuit. You know, so the air comes in from the forced draft fan through the air heater, supplied, you know, through the burners, and then to overfire the wind box, and we can have overfire air, and then it supports combustion, and then it leaves, comes through the convection passes, across the economizer, through the air heater, and then goes out, pulled by the induced draft fan through all the cleanup equipment. And we went through, figured that the other day, and then we'll talk our way through the water circuit as we come in from the economizer and get preheated, go to the drum, go to the water walls, and then the steam works its way through the superheaters, perhaps getting sprayed by an attemperator for steam control, and then winds up going out to the turbine. So we've got a diagram here in a minute that goes through all of that. So we'll see. So I think that's pretty much what we're going through here. And we're talking, we'll take a look at these. Make sure I covered all these points, furnace and convection pass. You know, that furnace, it's a large open area. It's lined with tubes, water wall tubes, got that water going through. Some of it's being converted to steam. And it, you know, taking heat out of your hot gases. So we're starting to cool the flue gas before it hits the convection pass. So we have to be concerned with particle accumulation. If we have a fuel that has any solid materials, and of course, if you know, we're also concerned with excessive metal temperatures, making sure that that flow is sufficient inside the tube, because it's that flow that's going to cool the tubes. Convection pass is made up of the superheater sections, the reheater sections, and the economizer. And that's typically this, pull this up. So the convection pass, once we come out of the furnace, then we enter the convection pass, and that's this horizontal section. And then the flue gases actually move downward. And then they continue. There's the economizer. That's the last liquid, or that's the last liquid gas. And then they move across the air heater. So, and then if we had NOx reduction, the NOx unit would be right in here before the air heater. So we might have to, if we added a SCR to this, we might come out here, go through the SCR, then come back in and go through the air heater to go out. So it depends what gas cleanup equipment that we've got. But that's the convection pass. Let me see, I think, oh, it shows it up here at the top. I'm not quite. There you go. So once we exit the furnace, then it's convection pass down and through all of these components and out. Okay, so all of this furnace and convection pass are constructed of these low alloy tubes that can withstand the high temperature. And they've got, in the convection pass, we'll cool them with steam, lower temperature steam. So that's also part of the steam heating. But we've got flow through all of those tubes. You know, in the water walls, it's a water and steam mixture, but in the convection pass, it's steam, lower temperature steam that's being heated. We'll cool those tubes as well. And of course, we have headers where we need to either split a single pipe flow into a bunch of different tube sections, or we need to take a bunch of tube section flow and put it together into a single pipe. We use headers to do that. Furnace wall tubes are the key steam generating components, welded together with steel bars for support. Superheaters, reheaters, inline tube bundles that increase the temperature of the saturated, start to superheat it. Reheaters also, the reheaters are probably receiving superheated steam. So, I don't know. Steel alloy material for operating at high temperatures. Design points, control steam outlet temps and keep steam metal within limits, control steam flow pressure loss. Difference between reheaters and superheaters is basically the pressure. You know, those superheaters see, you know, main boiler steam pressure. Of course, by the time you go out to the turbine and then come back, you've dropped, you've already expanded through the high pressure turbine, and so you've dropped a whole bunch of pressure. They might be, 400 or 500 psi instead of 1800 to 2400 psi through the high pressure turbine. Typical drum boiler, superheated outlet pressure 2700, while reheater outlet is 580 here. Kingston's lower than that because, Kingston's max is 1800. Often divided into multiple sections, that's superheaters and reheaters. And we can put attemperators in between some of those sections to blow some water or low temperature steam for steam temperature control. That's one of the means. We'll list some of those. This boiler bank, that's on this industrial boiler. That's, where's that tenor on that? Going the wrong direction. There we go. This boiler bank is right here. And this is on an industrial boiler. So they're showing this as large industrial power boiler. And we mentioned that before, but you've got your main steam drum up here. And it's feeding all of these water wall tubes, but it also has some additional tubes. And these are to generate additional saturated steam. This is your mud drum down here. And so your water will fall out of the drum down this backside because the gases are cooler there a little bit. And so you generate, and then it comes back up here, and we're just generating some additional steam in this little loop. It's called the boiler bank. Going to the boiler bank to make a withdrawal. Figure 10, yeah, we're talking about that. So I think that's, I've mentioned all that. There's the lower drum, the mud drum. Economizer, I think we've been over that before. Let's go up to the, So feed water's coming out of that high pressure feed water heater. When we did the thermo stuff, it's the one on the left. It takes the highest temperature extraction steam. We get a boost out of there. We come over here. We're going to boost it one more time. So that water is going to go through that economizer, and then it's going to be routed to the steam drum. So that's the max temperature we can get to the steam drum is what comes out of the economizer. So it's a flue gas on one side and liquid water on the other side. So it's not a two-phase situation or anything. Economizer. Yeah, we said all that. Okay, tube spacing, tight as possible to promote heat transfer while allowing tube surface cleaning. And so, again, if you got natural gas, you don't have to worry about that. I mean, you could soot it up a little bit, but natural gas boilers, you can take them offline and clean them pretty easy. But these coal boilers, wood-fired boilers, biomass is a mess. That, where was that? Huntsville, Alabama, the largest chicken rendering plant in the world. And you know what a chicken rendering plant takes? Have I told you all the life cycle of a chicken? It's one of my favorite digressions. Well, the complete end of the chicken, the stuff that Kroger won't take from the processor. I mean, Kroger takes what? The thighs and, the breast and the whole chicken, that you can buy and put in the little pot and boil it up and put it in the crock pot. Well, the chicken processor, those chickens come in, they've got feathers, they've got beaks, they've got feet, they've got blood, and they got guts. And you know what? The chicken is separated from all of those things at the processing plant. So if you're a chicken, that processing plant is not a good place to go. I've visited a few, and I can't say it's a particularly good place to visit, you know, but I guess it's interesting. Well, so all that stuff, they call it IC. This is something you won't learn in any other courses. IC is what goes to the process or the rendering plant. It's called inedible chicken. So it's everything that can't go to probe from the processing plant. Well, down there in beautiful Hanceville, Alabama, the largest in the world, they take that stuff, the feathers and the beaks and the blood and the guts, and they convert it, most of it, to high protein meal. So the name of this company is American Proteins. And then they make animal feed out of it. In other words, they feed the chicken back to the chickens and other animals. But anyway, these guys, they had big boilers because they have steam-driven kilns, and they put these feathers and beaks and claws, and they heat them up to 180, 190 degrees, and they just rotate them in these rotary kilns under temperature. And I guess some of the stuff turns into beautiful aromatics because it's not a place that you want to eat before you go. Because you won't maintain your breakfast long. They tell you on your first visit, don't eat breakfast before you come because we don't want to clean it up. Oh man, now, I never did puke, but I got it up here about almost to my, you know, the top of my throat 3 or 4 times, you know. But anyway, so the purpose of this story, other than I like telling it, is that they had this anaerobic, one's with oxygen. They had this pond where they put the blood and I guess some of the gut, I'm not sure what all, the stuff that they couldn't turn into meal. And it was a digester, and it would produce combustible gases. And they also got some chicken, somehow they could come up with some chicken fat, I think. But their boiler was designed to burn this stuff. You know, so they were gonna, hey, I mean, talk about efficient, they were gonna generate some of their own fuel, not all of it. The rest of it was natural gas. And so when they first opened the plant, they ran for about a month on chicken fat and digester gas. And they so fouled up their boiler with deposits that they couldn't generate any steam. And so they had to shut down for 2 weeks and clean all this gunk out of the inside of their boiler. And they said, never again. So, you know, sometimes renewables and all that stuff, it sounds good, but in the practice, maybe the systems are not adequately developed to handle it, which was the case anyway. Of course, this was probably designed, you know, 30, 25, 20 years ago. I don't know. But anyway, that was interesting to talk to them about their experience in trying to burn some of these alternative fuels instead of natural gas. And they couldn't get back on natural gas fast enough. Okay. So anyway, you know, design a boiler has to be to promote cleanliness, because if you can't keep it clean, you can't operate long term. Steam drum, we talked about that. Cylindrical, top of the boiler, 3 foot, 6 foot diameter, lengths to 100 feet. House steam water separation equipment. Purify the steam mix, replacement, feed water chemicals, provide limited water storage to accommodate changes in load. Keep that water stored at the top of the boiler. Drum level control we talked about, critical operating parameter. Okay, steam temperature control. So we need to know a little bit about how can you control your steam temperature. Well, the note, and this is from the B&W book, complex systems using combinations of recirculating some flue gas from the top or bottom of the furnace. So they have fans that can recirculate flue gas. Okay, so you know, if you took it from the top of the boiler, it's cooled down some from that which is being generated in the fireball. So you can recirculate some of that in order to, that will affect the heat transfer rates and will affect the steam temperature. So there's special gas passages at the back end of the boiler. We can adjust the combustion system, so you can certainly adjust the fuel flow rate. If you don't burn much fuel, you probably are going to tend to produce cooler steam. Adding water or low temperature steam to the high temperature steam flow, that's the attemperator, so we can spray into it. And the other thing we need to think about is how quick of an impact would this have on steam temperature? You know, for example, if you cut your firing rate in half, how long is that going to take to really affect the temperature of the steam that's being produced? It's probably going to take a little while, right? Because this is a massive boiler, stores all kinds of heat in the tubes and the metals and all that. So you cut the fuel flow rate in half, and so the fireball gets smaller, and you know, there's not the same heat flux. So, but you've got all this heat already in the tube walls and all. So, you know, that's not going to be an instantaneous change. Now that attemperator, man, that's throwing cool, you know, cooler steam or water directly into the steam flow. That's, I think, about the quickest that you got. Okay. Adjusting, you know, this recirculation of flue gas, you know, it's maybe on the same order as changing the firing rate, you know, I don't know. Not going to be instantaneous, not going to be as quick as the attemperator, you know. And so, you know, as an operator would be concerned about all that, you know, because if he's making a change, then he's going to know, well, is this something that, you know, I can get there in 30 minutes and everything's fine, or is this something I need to do like right now and get it done? Let's see, so spray attemperators, they're pretty commonly used. Large utility boilers, temperators use direct injection of water, low temperature steam, and are used for dynamic control because of rapid response. And this next bullet is about the attemperators. They're designed to resist thermal shock, located at the inlet to the superheater or between superheater sections. And that goes for reheaters too, for better. Because, you know, we don't want to be potentially spraying water into steam as it exits the boiler, because that water, something fouls up, it could make it to the turbine. And then we got another note down here, I'm going to skip down. Burner tilts. Okay, so especially, well, all burner, even wall fired or T-fired. You know, remember T-fired are in the corners, tangentially fired, and wall fired are just in the flat walls of the boiler. So those burners are on tilts, and they can be raised and lowered 30 degrees from firing straight out. So you can position the fireball vertically up or down inside the furnace by changing the tilts. Well, that's a pretty cute trick, you know? So we got those burners, and they're, I guess, you know, some kind of a hinge mechanism where they can push them down to move the fireball lower in the boiler, or they can tilt them up to move the fireball higher in the boiler. Well, that's interesting because, you know, if you move the fireball higher in the boiler, that's like not having as much boiler tube, you know, exposed to hot gases. So that would affect your steam temperature and your steam generation rate, okay? And if you push it down, it's like you're exposing more water wall tube to the fireball and the hot gases above the fireball by pushing it down. So what these guys do is they use this in conjunction with the soot blowers, okay? Because as the boiler starts to get dirty, you know, soot's up, you got ash and stuff, whatever, on the outside of the tube, you can't transfer as much heat. So as you can't transfer as much heat, you either can't make as much steam or you can't make it as hot, some combination thereof. And so they start moving the tilts down. You know, let's say, you know, with clean boiler, you start off with neutral tilts or maybe somewhat up, depending on, you know, the amount of steam you're producing. Let's say if you're at 100% load, you're probably about horizontal. If you're at reduced load, then you can afford to raise them. So you start out with a clean boiler with your tilts raised a little bit. As the boiler starts getting dirty, you know, if you want to maintain, you know, constant operation, you got to start lowering the fireball. So the tilts come down, come down, come down, come down. When they get down to about minus 20 degrees, I've been told that last 5 degrees doesn't do much, then they start getting ready to initiate a soot blowing sequence. And so then, and for a soot blowing sequence, they have to figure out, well, what's dirty? Is it the furnace tubes? Is it the primary superheater tubes? Is it the reheater tubes? Is it the secondary superheater tubes? Is it the economizer? You know, what is fouled? It's not likely it's probably all going to foul up at the same time. So they've got different controls and they've got different sequences to blow different parts of the boiler in order to figure, and they have to look at different temperatures throughout the boiler and pressure drop, because as we foul up, the pressure drop at a given flow rate through different sections of the boiler will be different. You know, there'll be more pressure drop. So by looking at temperatures and pressures, they figure out, okay, we need to blow the first part of the convection pass. And so then they program a sequence in the soot blowers and clean those. They get everything clean, all other things being equal, the tilts then pop back up again. So it's a combination of management between the tilt position and the cleanliness in the boiler as determined by temperature profile and pressure profile. So it's pretty interesting. You know, it's interesting to talk to the operators about it. You know, I give you my take, and then if we can make it to Kingston, you can get off to the side and ask the operator, hey, that old man over there thinks you do this, and then you can ask them what they really do. Say, how do you really do this on soot blowing, or, you know, controlling tilts and all that sort of thing. And, you know, I've been making that trip a long time, and sometimes you get an operator and they basically parrot back what I say, and man, I go, yeah, baby, I got this. You know, and then you get some other operator and he says something 100% different. I'm going, oh crap, I hate this trip. But you know, that's all kind of the fun of the game. Okay, so I would include that the burner, tilts, and soot blower affects the steam temperature. I mean, it may not be a primary control mechanism, but you've got, say, flue gas recirculation, you've got firing rate, you've got attemperators, and you've got burner tilts. All of those things affect your temperature, okay? And then there's a note in here about the air heater. Some people don't even really consider the air heater part of the boiler. Other people do, you know, but it's the last heat transfer surface that the flue gases see before they exit the boiler for cleanup and disposal. That's good. So on the air side, 40-degree increase in temperature is nominally 1% boiler efficiency. So that's a good number to know, you know. So on that air heater, 40 degrees is 1%. And so that's the increase in that incoming air. If we can boost it 40 degrees across the air preheater, then we pick up one point in efficiency on the boiler. If we could pick up 80, we'd pick up roughly 2%, something like that. So that's a good number to know. Okay, I think we're, yeah, I don't think this, oh yeah. There's this down here. Let me see. Do I have that? I think I have that. cut and pasted at the bottom of this one. Do I? Yeah, here we go. I got a bigger version. Okay. Okay, so this is kind of the culmination of this boiler discussion. This is pretty good though. So what he's got here, and he doesn't have all of the components by far, but so we've got the water circuit, we've got a two-phase circuit, which would be steam and water together, and then we've got the superheat circuits, okay? And so you can kind of follow in a little bit. So the water circuit, you know we've got our feed water coming in to the economizer over here at A. So that's A, and then it goes through the economizer and is to B. And then from B, it's going to be piped to C, and then over here to D. So they're showing the pipe going up the convection pass. I'm not real sure where this runs, if it's outside the boiler or whether there's an opportunity to pick up a little more. But basically, I think these are headers. And so, we come in a pipe and we split into a header, and we split it apart a little bit to go through the heat exchanger. And then we put it back together again. And then we pipe it up here, over here to D, and we put it in the steam drum. So that's your feed water flow. So that was pretty simple, okay? And then you got your two-phase circuit, which starts at D, E, F, G, H. So D, we're up here in the steam drum. And we're gonna, well, now see, up here there is two-phase, we have the steam separators and all. What falls out of the bottom here is just water, because this is your downcomer. But this is the circuit that generates the two-phase, certainly. And then so we come down here to the bottom and we spread out. And then we enter the water wall tubes and we come back up through. And so here's your furnace, two-phase flow. We're cooling the tubes, certainly, as we come up through here. So then we come up to G and G, and I guess to H, where H is where the steam exits. Okay, so that's how they've got that tagged. Okay, so that's the two-phase circuit. And then the steam circuits, there's actually a couple of them here. Let's see, so we're coming out at H, and we come down, and so one circuit comes down here and splits and goes to I. And so these are steam-cooled roof tubes. And so like I said, this entire enclosure has to be cooled. And so some of this steam, this saturated steam, this is, it's hot by our standards, but, this is maybe, what, 600, between 600 and 700. This stuff is going up to 1,000. So, 650 degrees, 670 degree steam is cool, in the boiler world, in at least the high pressure boiler world. So we're going to use that for some roof cooling. And then we're going over here to L. And then we're going to come down to the primary superheater. So we come out with cold steam, we cool the enclosure, and we go to the primary superheater, which is way down here, almost at the end of the convection pass. And so, your flue gases are getting colder, right, as they come down through here, because they're going across all kinds of heat exchanger surfaces, they cool them down. When we get down here at the bottom, I don't know, we're probably 750, maybe 800, depending on the load and all. And these gases over here are pushing 3,000 degrees, coming in the middle of that fireball, maybe hotter than that. Okay. So, so this steam comes out, and after it does roof cooling and the enclosure cooling, then it's coming over here to the primary superheater, where we do, a good bit of superheating. That gets us to N. And then look, we're going to come up over here and we're going to go through in a temperator. So we're going to do steam temperature control, dynamic, quick reaction here at O. and then P, then we're going to go down through the secondary superheater, which is seeing really hot gases, right? Because they're coming right out of the furnace here. So the secondary superheater sees the hottest gases of any of the superheaters or reheaters. So it goes down through here and then exits, gets put back into a single steam pipe, and off it goes to the turbines. Okay, so that's one of the steam circuits. The other one comes down here, it goes H, from H it leaves the drum and comes down here to J, and this is more, what do they call this? Steam-cooled convection pass. So this stuff, instead of the roof, is cooling the convection pass, these tubes that, contain everything, the flows. So then it goes from J to K, and then it comes back out here, so we're K, and then we go M to N, so that's then the primary superheater, so it goes through the primary superheater, and then it goes, has the same path. Whoops. So it's coming back up through the attemperator, through the secondary superheater, where it gets topped off in temperature, and then out to the turbine. So that gives you, a pretty good idea. I mean, we don't have to know every bit of this, but, we need to have some kind of an idea how these things operate and all. So, I mean, a lot of, all these sections would still be there regardless of the fuel, on a utility scale boiler. I mean, you could be burning natural gas. You're going to see the same arrangement. You're just going to see tighter tube spacing, and you're not going to see soot blowers, that sort of thing. So there are some differences, but not a tremendous amount. Okay, I have just a few minutes. So that's the end of my boiler discussion here. Yes, sir.
So whenever we're doing like the thermodynamic analysis of all that stuff, all of that takes place in that one little section from like stage 2 to 3, basically. Is that basically what's being shown right here? This is the boiler.
Well, okay. All of this occurs, that's a good question. And this, okay? And to give you an idea of scale, remember, see the little person standing down there in the basement?
Yeah.
Okay, so I gotta make it smaller yet. So, I mean, this is a 1,300 megawatt, so maybe they're not all quite this big, but basically, all of that stuff we just went through occurs in this box. There's your economizer, superheater, secondary superheater, reheat superheater, convection pass, furnace, the temperators, it's all there, Now, I mean, look at the size of that guy. I mean, this was about like a 4 or 5 story building, so, and it all occurs within that boiler. Yeah. Okay. Is that?
I guess my question was more like when we do the analysis, we have the compressor, the boiler, the turbine, and the reheater. This is all that boiler section.
Yeah, exactly.
Okay.
Oh, yeah.
So we see it comes in at a certain pressure and leaves it at a higher temperature. All of this.
Oh, exactly. So when we were working thermal problems, we had feed water, we'd leave the last, feed water heater, that pump we'd have our last pump that was pumping everything back to the boiler. So it comes in up here at the steam drum. So that's the feed water in. And then you got your main steam line. This doesn't show it. Well, here's your main steam line. We have a condition going out. Yeah. And all of this stuff is basically in that box we call the boiler.
So it's a little bit of an oversimplification.
Oh, yeah. I mean,
Because a lot of these things will probably have efficiencies too, right? Like, is that the case?
Oh, yeah.
So it's, even when we do that from like, I guess if we have the temperature though, that kind of accounts for the.
Well, I mean, if you have a measurement on your fuel flow, and you know the characteristics of your fuel. You know how much energy that you're putting in. If you have, you can measure the temperature and the pressure of the feed water coming in. You've got a certain rate of main steam flow out of this at a temperature and pressure. You've got reheat steam in and out, temperatures and pressures. I mean, and if you have any pumps like these polarizers or stuff like that, that has electrical energy input, you can measure that. You've got your pump energy, you can measure that. But as far as what the thermal efficiency of the boiler is, you know, the useful energy out in terms of the steam flow divided by the energy input in the fuel. And I mean, it's just what we've done. Now, you know, and we look at that. Here, I'll show you. Now, I mean, you know, the real world always turns out to be, you know, much more complicated. So here. So I'm doing a steam workshop for TVA tomorrow. I think I left that slide in here. Or did I cut it? I don't know. I didn't cut it. I cut it out of this. Oh no, here it is. Okay. This is perfect. Okay. So out of the ASME Power Test Code 4.1 is for efficiency testing on large boilers. And you know, you can do the classic boiler efficiency, we talked about that, or you can do the loss method. So you can calculate all the losses individually and take 100% minus the losses. That's the way this really gets done out there in the world, because you usually don't have really good measurements on fuel flow rates and that sort of thing, and even steam flow rates. Sometimes the flow measurements are not accurate enough to get a good boiler efficiency. So these are all of the potential losses for a large utility scale boiler. And of course, there's PTC 4.1, which I will probably send you a copy of towards the end of the course, goes through in great detail and gives equations and ways to calculate each one of these. Because this is an official way to calculate a boiler efficiency, like for a warranty evaluation. You know, TVA buys a big boiler, it's supposed to be 89% efficient under certain operating conditions, and they operate it for a little while and they say, nah, this thing's not that efficient. And so all of a sudden the lawyers get involved, and so they hire Cunningham Engineering to come in and do the official boiler test. So I come in with PTC 4.1 and say, okay, boys, this is the official, you know, performance power test code. This is what we're going to use. And you go through and you figure out, now, not all boilers will have all of those losses. You know, if it's a natural gas loss, you know, you're not going to have any atomizing steam, you know, because you don't have to atomize. So, you know, so you go through this and you sit down, you know, a natural gas not going to have any soot blowing. So that's a loss you don't have to calculate. If it's a coal boiler, yeah, you probably got to do most of this. But I mean, look at all of the different ways. And of course, you don't know at this point exactly what all these terms are, but you know, this is LOI, right? Unburned carbon and refuse. We talked about LOI. Heat in dry gas. So that's heat in the dry flue gas. Moisture in the fuel. You know, you put in wet coal, guess what? That's an extra loss, because that water in that fuel is gonna get evaporated, and that's taking energy to evaporate it, and that water is gonna just leave the system as water vapor. That's an energy loss. So that hurts your boiler efficiency. You know, put a damn tarp over your coal pile and keep it dry. You know, moisture in fuel, moisture from burning hydrogen. I think that's the water loss for the hydrogen that's in the fuel. I believe that's what they do. Some of them, I mean, I hadn't looked at all this stuff in a while. Moisture in the air. You got water coming in the combustion air because there's humidity out there, you know. All of this stuff, unburned hydrogen, if you got unburned fuel, shell loss, radiation and convection. I mean, all this stuff, soot blowing. If you got cooling water, say there might be parts of the boiler shell you have to pump cooling water through so it doesn't get damaged. You know, that's a loss. So yeah, I mean, this is what the real world is about at the utility scale. Yeah. Okay, well, that was a great question. And I droned on long enough so that we'll just stop right here. We can start the turbine article and some of the fracture mechanic stuff after the test. So I'll be working all weekend. If you have questions about the test, I don't really know, and probably until sometime Sunday, because I'll be working on it. Pretty busy tomorrow, so it's probably going to be Saturday and Sunday putting that test together. So don't really know. I mean, I have some intentions in my mind, but pretty much just, you know, small individual thermal problems, you know, maybe like 15 of them or something, you know. I want to keep you busy, you know. I want to not give you enough to keep you busy for the whole time. Yeah.
If we have questions during the test, do we email you or you have Zoom?
I would say just email me. That's probably best. I mean, you know, I mean, the way I intend to write these questions, I would hope that you wouldn't have. I mean, you may not know how to work one of them, but I'm probably not going to answer that question. You know, but if you're confused about something, certainly, you're free to email me, and I'll make, you know, I mean, I'll be sitting. I probably won't be sitting in here because nobody will be in here, but I'll be sitting in my office watching. Okay. All right. So yep.
My question is for the test questions, that'll be like the thermal problems. Will you give us like the enthalpies or entropies that we need, or that be something we have to find in a table?
Nope, you'll have to find them.
Okay.
Well, I don't know. I mean, you know, we did one of those big homework problems. They gave you that. So, I mean, I guess I haven't really thought about it, but I could give you, you know, a complicated cycle and give you all the enthalpies and then ask you to calculate an efficiency or something. I mean, you know, once you have the enthalpies, the rest of the calculations are pretty quick, you know, if you know what you're doing. It's finding those blasted enthalpies that takes forever. So, you know, I mean, you need to be ready to find your own properties. And probably what I'll do is for the utility rates, I'll email you out a utility rate file to use to answer any rate calculation problems. You know, so that we're sure everybody has the same rates. You know, it's not going to go well if you're using a different rate file, you know, than the one I use. Okay, good question. Any others out there? Okay, hearing none, I'm going to cut this off. Everybody has a great weekend. See ya.